In this lesson, we are going to study one of the most important applications of systems. It's called linear programming. Linear programming is a proven process for maximizing or minimizing a function's values when it is limited by some group of constraints. Most of the situations that we will look at, we will be attempting to maximize some value, but there are occasions when linear programming can be used to minimize a value. The function that we are going to optimize or minimize will be written in three variables, and the constraints are all linear inequalities. So to use linear programming, or in the case of finding a maximum, sometimes you'll hear it referred to as linear optimization, you need three things. Two of them will be given to you, and one of them you will find. The first thing that will be given to you, or you'll be given enough information to determine what it is the objective function. The objective function is the function that we write, and we recognize that's what we are trying to maximize or minimize. Most of the time, you will see the objective function written with the letter z, as that will be the third variable that will fluctuate based on x and y. Sometimes you'll see it with a different variable, maybe something like c, as a representation for the cost. And then occasionally you'll see it written like this, with a capital F and an x and a y in parentheses. Now, if you remember, this was just a way of naming a function. And I like this representation because sometimes when you see the x and y in there, you might think it means something else. Maybe it means a point. And in this case, it actually does mean a point. But we have two inputs for this function. We're going to have an x input and a y input. So it's almost as if you're thinking back to our functions work, we're going to have two independent variables instead of just one. And z, the other one, or in this case, the function named f, is going to depend on both of those. The other main part of a problem that you are going to be given in some way, shape, or form are the constraints. X and y are going to be limited by some conditions. They'll say maybe x can be at most this or at least this. X and y together can be at most this. Depending on that information, your responsibility comes in writing a system of inequalities to represent those constraints. So it's not as if the constraints are necessarily going to be handed to you. You may have to interpret the information given to you in a problem and work through the creation of the system. In the first example we're going to look at, I'm just going to give you one, but that can fluctuate based on the scenario. And then the last thing that you'll get after you've already worked with the objective function and the constraints is you will look for a graph of those constraints. Notice that we are not graphing the objective function. Despite the fact that there is a third variable, we are not graphing this in 3 dimensions. This objective function will respond to what is happening down here. So as we graph the constraints, as we graph that system of inequalities, that objective function will respond to those values. And in particular, we're going to be looking for the corners and the vertices. So here's an example of what an objective function, constraints, and a minimization problem might look like. They'll give you, or we are given here, an objective function. This objective function is z equals 2x plus 2y. You might sometimes see this written as fx of x and y, 2x plus 2y, since this function is responding to both of those variables. And here are our constraints. These are two very popular constraints. This is just ensuring that x and y are non-negative. Because a lot of linear programming problems happen in context, there's not a lot of context floating around where the negatives will be useful. And then for this particular case, we have two more constraints. You'll notice they're not written in slope-intercept form. They're not written in any kind of form. They are in standard form, but they can be in all different kinds. Worst case scenario is you can change them so that they're written in the form that you like. So for example, if you don't like that version of the third constraint, you simply can solve for y, and now you might have a version that you're a little bit more comfortable using. We have a slope of -1/2. We have an intercept of 5/2, and that's a fairly easy graph to make. Same thing with this one if you wanted to solve it for y. But it's these 4 constraints that are going to go into our graph, not the objective function. The objective function is going to respond to the picture that we draw. It doesn't need to be part of the picture. So let's see what that graph is going to look like. Now, it can be a little bit difficult to interpret this, especially when it's already drawn for you and you don't see it pieced together. But just a couple of reminders. Here's x is greater than or equal to 0. That's our vertical line. Here's y is greater than or equal to 0. That's our horizontal line. And you can already see why it's nice to use some kind of technology to draw this. I'm even drawing it freehand, and it's not perfect. Here's our line that we solved for y. There's our intercept of 2.5 with our slope of -0.5. We're coming this way. And then this one is the other one that we didn't solve for y, the x minus y greater than or equal to 2. So as you're coming this way in each, or sorry, less than or equal to 2, excuse me. But as you're doing this and you're graphing them and you're picturing that I'm to the right of that line, I'm above that line, I'm below that line, and I'm above this line, that means that this is going to be our quadruple shaded region. And I've highlighted the corners because in a linear programming problem, these corners are the most important points. They are the points that we will test to determine where our maximum occurs. Now, this process was proved a long time ago, about 70 or 80 years ago. The proof of this and the reason why this works is a little bit beyond the scope of this class, but you are welcome to research it. I would encourage you to research it, but it is a little bit beyond what we're going to see in this class. So I want to take the moment just to stop and see what's happening here. These are all the points that work in these 4 constraints. But for a linear optimization, maximization, whatever you want to call it problem, we are only interested in those points that are on the corners. And that's what was proved as being true. That maximum or minimum of the objective function has to happen at one of those points. And the best part about this is, just as a reminder, the objective function isn't in here anywhere. We didn't graph 2x plus 2y. We couldn't. It had 3 variables in it. It would be impossible to graph it in a 2-dimensional space along with these other lines. So all we did was base our graph off of those 4 constraints. If I changed the objective function but left the constraints the same, the picture would look identical. The objective function had no bearing on the picture. Where the objective function has bearing is when we go to test all of those points. When we test those points, we are ensuring that we actually found the maximum or minimum. So we're going to take these points, here's our x's and here's our y's, and one at a time, we're just going to sub each one of those x's and y's in to their respective spots. And we're going to evaluate each one of these expressions and see which one has the largest value. This one is 0, this one is 4, that one is 8, and that one is 5. Based on the tenets and the proof of the linear programming, that's where our maximum is going to be. So the max for z is at the 0.31, and the value is 8. Linear programming guarantees us that the maximum will occur at one of those corners. If you can graph the constraints and you can find those corners, it shouldn't be that bad in terms of finding the maximum or minimum. And if you do not have a graphing technology available to you, you can still find the intersection points. You know that this line and that line intersected at 0,2.5. You could solve a small system of equations to find this intersection point over here. You could find solve a small system of equations to get this one. You know that the 2 0 lines are going to cross at 0, 0. So there's algebraic ways to find these points. You can solve small systems in order to find those points. But if you have graphing technology available to you, finding those points is significantly easier. And then we just go from there on the objective function.